I'd just like to thank the Institute for giving me this opportunity to make this presentation, and it's on calculus. And of course you'll all know that calculus hasn't got a very good reputation worldwide. It's considered a very difficult subject, difficult to understand, difficult to do it, and I'm hoping that what I'm going to show here will offer an alternative to this difficulty. And I'd like to suggest that calculus can actually be introduced much earlier than usual and in a very simple way that's easy to grasp. Many subjects like geometry, for example, are introduced early on and then they're developed from there step by step. So there's no reason why we shouldn't be able to do the same with calculus. It starts at a later age, at a quite advanced level with its own notation and terminology and everything, and most people get put off by it. But it's also a very important subject. It's got many applications, not just in mathematics and science, but economics, architecture and engineering and many other subjects. I'm going to first of all give you a little overview of the structure of this talk so that you know where you are. I'm going to first of all mention the prerequisites which I think would be needed for the child to take this material. And then I'll go on to how you can work out gradients. Gradients, of course, are very important. They deal with rates of change, and rates of change, of course, are everywhere. Everywhere things are changing, and if their rates can be measured, we can mathematically handle them and make predictions about the future and all kinds of interesting and wonderful things. And then a brief comparison with the contemporary approach, and then another way of working out gradients, pointing out a certain ratio that's very useful. And then I'll go on to area under a curve, which is the other side of calculus, because calculus, as you probably know, has two branches. It's the gradients, called differentiation, and the area under a curve, which is integration, and they complement each other. And then a comparison of the contemporary approach there, and then a summary. So that's all that's going to be. Prerequisites. What do children need to know to be able to do calculus, really? Well, actually, you just need a basic understanding of algebra, as you'll see the sort of algebra involved as we go on. And basic graph work, students should know about the parabola and drawing it, and what gradients are. And then limits. Limits are very important, and actually we're all aware of limits, and children are aware of limits. They know there's a limit to how high they can jump or how long they can hold their breath for, things like that. And it's easy enough to make some mathematical connections with those ideas. For example, you could think of a triangle ABC, and you want to know the limit of, say, BA as A goes towards and merges into C. And of course the answer is BC. BA merges into BC as A approaches and merges into C. Another example is a secant is a line that just cuts a curve like that in two places. And you can imagine here that Q may move around the circle towards P, and the secant changes because of that. And you can see that as Q approaches P and merges into P, the secant becomes the tangent at P. Okay, you can demonstrate that quite easily, but it's fairly obvious to most people. And so we do a bit of work on limits to get students familiar with the idea that we're going to use later. Also the graph work, in particular I'm going to be using this equation, which you're all familiar with, I'm sure, for the difference of two squares, P minus Q times P plus Q. And in fact, there are other equations too. This one's for the difference of two cubes, which is also P minus Q times another factor. And there are actually a whole range of these, which I'm going to come back to later on. So let's get started. Gradients. Let's take a very simple quadratic, the quadratic y equals x squared, a simple parabola that goes through the origin. And let's suppose you want to find the gradient of the secant that goes through those 2 points, S and T. let's just take a couple of numbers. Let's take 2 and 5. They're the x-coordinates of S and t. The gradient of the line ST is going to be the height of this triangle divided by the base. That's a definition of what a gradient is. We can take it as a definition. And the height is simply the difference of the y-coordinates, and the base is simply the difference of the x-coordinates. So if x is 5, then y is going to be just 5 squared. And if x is 2, y is going to be 2 squared. And so the difference of the y-coordinates is going to be 5 squared minus 2 squared, divided by the difference of the x-coordinates, which is 5 minus 2. So we have 25 minus 4, which is 21. 21 divided by 3 is 7. We get 7. And we may notice that the 2 plus 5, the x-coordinates which were given, adds up to 7. 2 and 5 is 7. And we could do more examples to verify this and show that it was true for the curve y equals x squared, that the gradient of a secant is very easy to find. You just add up those two x coordinates. Another way of verifying it, in fact proving it properly, is to call the x values I gave you there p and q. So now we've got p and q. And so again we're going to find the difference of the y coordinates divided by the difference of the x coordinates. And so the gradient of the secant is going to be p squared minus q squared, because now the y-coordinate here is p squared and the y-coordinate here is q squared. So the difference is p squared minus q squared over p minus q, the difference of the x-coordinates. And of course we can factorize the p squared minus q squared, as I showed you before, and we can cancel p minus q to get p plus q. And that proves the results, that you just add up the x-coordinates to get the gradient of the secant. Now we're going to go further from here. We're going to work out the gradient of the tangent, because we know that as s approaches and merges into t, the secant becomes the tangent. And so the gradient of the secant will become the gradient of a tangent as s merges into t. But as s merges into t, q will become equal to p. Q will get closer and closer to p and finally become equal to p. And so for our equation of the secant, we're simply going to put q equal to p, and we get the gradient of a tangent is 2p, p plus p. Or, because p is just an x-coordinate, we can give 2x. So this is a proof that the gradient of y equals x squared is 2x. You just double the x-coordinate to get the gradient at that point. Now, I'd like to just quickly show you the traditional proof for this. I'm not going to go through this. There's not really much point. Either you know it or you're likely to be confused by my explanation. You can see the symbolism is quite intricate. You've got the limits featuring there. You've got deltas, delta x, delta y, which makes it more complicated. This is the standard proof that the gradient of y equals x squared is 2x. So coming back here, let's see if we can extend this for cubics. So cubic. Here's a cubic, y equals x cubed, and there's the secant, and the x-coordinates again are p and q. And the y-coordinates are now p cubed and q cubed. So the gradient of that secant is again the difference of the y-coordinates over the difference of the x-coordinates. So it's p cubed minus q cubed over p minus q. So this corresponds to what we had up here for the quadratic. And we're going to do the same thing as before. We're going to factorize the difference of cubes like that, cancel the p minus q, and we get p squared plus pq plus q squared. That's the gradient of any secant for a cubic, for the cubic y equals x cubed. And it has again a nice symmetry. That corresponds to the p plus q we had up here. And now we've got this. And we're going to do the same thing as before and work out the gradient of the tangent from that. And we're going to do the same thing. as this point here merges into this point, the secant becomes a tangent and q becomes equal to p. So we simply put q equal to p here. We get p squared plus p squared plus p squared, which is 3p squared, which becomes 3x squared. And so that's the standard result for the gradient of a cubic. And we can take this further. So there's the difference of two squares, difference of two cubes, difference of 2/4 powers. Now you'll see, we're going to look for some patterns amongst these equations. And of course they go on. You'll see that when the p minus q goes under the left-hand side there, we get our p plus q. Gave us the 2p, which gave us the 2x. For y equals x squared, we had the gradient was 2x. For y equals x cubed, the gradient was 3x squared. For y equals x to the fourth then, we look at this bracket here, this last bracket, and we see that when q is put equal to p, we get p cubed 4 times. So we get 4p cubed, which becomes 4x cubed. Now those numbers, those coefficients, 2, 3 and 4, are just the number of terms in the bracket, because we've got 2 terms here, which gave us that 2, then 3 terms, and then 4 terms. And that number is also the power on the left-hand side. So for x to the fourth, we have a coefficient of 4, and the power on the x cubed here is always going to be 1 less than the power on the left-hand side. So where we're dealing with y equals x to the fourth, we know we're going to get an x cubed in the gradient formula. So from that, we can generalize to this statement that for y equals x to the n, the gradient is nx to the n minus 1. And that's the standard result. And we can go further and get for y equals ax to the n. So if there's a coefficient in front of the x to the fourth or whatever, then we can handle that too. And that's easy to understand, because if you take a curve, say y equals x to the fourth, and you put a 7 in there, you've got y equals 7x to the fourth, all that does is stretch the graph by a factor of 7 vertically, and so all the gradients will get 7 times bigger, and that accounts for the a appearing on this side here. Otherwise, this equation is the same as this equation. The a simply is carried forward. So we can find gradients for all these curves. So just to summarize this up, I've called this the secant tangent method, because we start with the secant and it turns into a tangent. And the idea is to choose 2 points on the curve with x-coordinates, say p and q. So in the example of y equals x squared, we chose s and t, and we then find the gradient of the secant by just doing the y difference divided by the x difference, and then we simply put q equal to p, and then put p equal to x, and that's it. And that will apply to all curves of the form y equals ax to the n. And in fact, although I'm not going to go through it here, we can also apply it to polynomials as well. And it also applies where you've got negative powers. You can use the secant tangent method there too. So 3x to the minus 2, you can also do it. Or if you've got fractional powers, here we've got a power of 5 over 2, if we bring the 2 over there. And we can handle that as well with the secant tangent method. So I'm going to show you now an alternative way of getting gradients that's actually quite useful. So if we just return to that parabola y equals x squared and the secant, we know the gradient of that secant. If these x-coordinates are minus 3 and 7, we simply add those numbers up, remember? And so we get 4. The gradient of st is 4. It's very easy. Supposing we let s move around the curve towards t, there's 2 special positions it can take. One is where it's at the origin, as shown here, and the gradient of that line, I'm going to call it the origin gradient, is x, because it's the sum of the x-coordinates, as you know, and here we've got 0 plus x, which is x. So the gradient of that origin line is x. Now if S carries on moving around the curve towards t and eventually merges into t, then we know we get this gradient, this tangent, and we know that the gradient of a tangent is 2x. Just to work that out. And so what we notice here is that 2x is twice 1x. And that factor of 2 is in fact the power here in the x squared. In other words, if this had been y equals x cubed, then the tangent gradient would be 3 times the origin gradient. So here, the tangent gradient is twice the origin gradient. We proved that here. And if y equals x cubed, then the tangent gradient would be 3 times the origin gradient. And this is a very useful formula. And so it means that the ratio of gradients is n for y equals ax to the n. It all depends on this power here. The ratio of gradients is n. It's equal to that power for all curves y equals ax to the n. So even if we have a factor, a coefficient in front of x to the n, the ratio is still there. Now I'll just show you an example of that. But first I'd just like to point out that there's another way of getting the gradient, the origin gradient, because if you want to know the gradient at point t, say, then it's simply going to be the y-coordinate of t divided by the x-coordinate of t. So if this was the point, say, 1, 4, then the gradient would simply be 4 over 1. It's just a matter of dividing the coordinates of t, as you'll see in the next example. So we said that the tangent gradient divided by the origin gradient is n. And we can write that as the tangent gradient is n times the origin gradient, as pointed out, is simply y over x. So, suppose we're asked to find the gradient of y equals 3x to the power 4 at the point 248. Well, what's our n? Our n is just that 4 there. And what's our y over x? It's simply 48 over 2. So, the answer is 4 times 48 over 2. So that's 96. Another example, here we've got y squared equals 12x cubed, and the point is 318. What is the value of n now? Well, it's got to be in the form y equals ax to the n, and I've got y squared, so I need to take the square root of both sides, telling me that the power on x is going to be 3 over 2. So the answer is going to be 3 over 2 for n times y over x, which is 18 over 3. That comes to 9. So it's very easy to work this out, and the nice thing which we're coming to next is that this ratio of gradients equal to n ties up with a ratio of areas, which is equal to n in the next section. So moving on, suppose we have a line, a straight line drawn from the origin, like this, y equals ax, and supposing we drop perpendiculars from some arbitrary point onto the x and y axes, like that, then you would agree that the ratio of areas here is 1 to 1. The areas are equal. The triangles are congruent. Now, supposing we want to draw a line from the origin, but we don't want to have a ratio of 1 to 1, because we know 1 to 1 will always be a straight line. Suppose we want a different ratio, say 2 to 1. What kind of line could I draw from the origin that will give me a ratio 2 to 1 instead of 1 to 1? It's a nice question, and the answer is y equals x squared. If you choose any point on y equals x squared and drop perpendiculars, then the ratio of areas is 2 to 1. And in fact, this goes further, because if y is x cubed, the ratio is 3 to 1, and so on. So, just to take an example how we can use that to find an area, suppose the value here is, well, 3, then, well, suppose we want the area under the curve there, where the 1 is. We know that because the ratio is 2 to 1 there, the area we're looking for must be a third of the whole rectangular area. This area we can find, and this is going to be a third of it, and we can find that rectangular area, because we know the y-coordinate, y equals x squared, and so this is simply the square of 3. So the area of that rectangle is 3 times 3 squared, and we just take a third of that, and we get the area. So it's very easy with this result to find areas under curves. Even quite young children can cope with it, and of course we get the other area as well. This area will be 2/3 of the whole rectangle. So the ratio of areas is n for y equals ax to the n. Here's a proof of that result. Suppose we've got the curve y equals x squared and we've got 2 points p and q on it, and we want to show that the ratio of areas is 2 to 1. I'm going to make 2 rectangles like this. So I'm going to find the area of the rectangle on the left there, where B is, and I'm going to write down the ratio of areas B over A. So the area of B is the base, which is Q, times the height, which is P squared minus Q squared, difference of the y-coordinates, over A, the area of A. I'm going to take that bottom rectangle there, and the base is P minus Q, and the height is just Q squared. Now we can cancel a Q here, cancel a Q, and we can factorize the P squared minus Q squared like we did before, and we get P minus Q times P plus Q, and the P minus Q will cancel. So what do we get? We're going to have P plus Q over Q. So that's the ratio. Now what I'm going to do is, as before, we're going to let Q approach P, so that little q approaches and becomes equal to little p. And what happens then? Well, the ratio will get more and more to equality of that ratio. And what happens over here is that we're going to get 2p over p, which is 2. So this is going towards the value 2. So what that shows us is that as q goes towards p, we can have a very narrow strip, vertical strip, and the horizontal one corresponding to, or have twice the area in the limit. And we can suppose that our areas A and B are composed of millions, infinite number of little strips, each one of which of the horizontal strips will be twice the area of the corresponding vertical strip. And so that really proves the result, and in fact also proves that the ratio is 2 to 1 for the whole area, under or to the left of the curve, like that. Now I think I've got, yes, the contemporary approach. Again, I'm just going to put it here. This, like the other one, this comes from a book, and you can see the notation, the diagram, and the proof. The argument is actually quite, well, I can't say convoluted, but it's not that easy to follow. It's quite subtle. So moving on, these are our diagrams from before, and I'd like to just talk about the area between limits. So suppose you want the area A under y equals x squared between the limits x is 4 and x is 5. Well, you can suppose that these two areas together, what we called A and B before, is the difference of the big rectangle minus the small rectangle. The big rectangle is simply going to be 5 times 5 squared, because this is 5 squared here, because it's y equals x squared, and the area of this rectangle is 4 times 4 squared, because again we have to square. And so what we end up with is the area is the difference of cubes. Okay, 5 times 5 squared is 5 cubed. The difference of cubes gives the total of those areas, and so what we want is a third of that. Okay, this area here is a third of the whole area here, and so I've got the area there as the difference of two cubes, and so I find a third of it. I'm going to take this a little further. Let's take a straight line, and the limits are the same. So the area this time is the difference of the squares. Because the line is y equals x, the y and x coordinates are the same. So the outer rectangle there, the outer square, has got an area of 5 squared, and the inner one is 4 squared. And I need to work out a half of that because the ratio is 1 to 1, and so the area under the curve is a half. So we see this follows a nice pattern, and we can in fact extend it further because we can work out the area under a straight line. In this case, it's simply the difference of the x-coordinates, because the area up to that line x equals 5 is 5, the area up to x equals 4 is 4. So it's the difference of the x-coordinates, and so it's 1 over 1 times 5 minus 4. And so of course we can extend this pattern to get higher and higher powers. And for y equals x cubed, as I mentioned before, the ratio is 1 to 3. And again, the a factor is not a problem, because if you compare y equals x cubed with y equals 7x cubed, one is simply a stretch, 7 vertically. Everything gets multiplied by 7 vertically, everything horizontally stays the same. And so all the areas will be 7 times more, but the ratio will be the same. If you multiply by 7, you'll get 21 times the area here and 7 times here. The ratio is still the same. And again, we can apply this method where we've got fractional powers, like 2 over 3 for the exponent of x. Then we get a ratio of 2 to 3. So there are a lot of ways of extending this too. And also polynomials. We can work out areas under polynomials in a similar way, which I obviously can't go into here. And so just to summarize, we have the secant tangent method, and explained that in some detail, and it has lots of applications. And from there we have this ratio of gradients, which has useful applications and compares nicely with the ratio of areas for y equals ax to the n. We can extend that to polynomials and negative and fractional indices. So in all of this, I have not used any complex terminology. We haven't talked about differentiation, integration, dy dx, so we haven't got all the nasty delta symbols and the integral sign and all that. So it is possible, I would suggest, that we can teach calculus to quite young children without confusing them with the terminology, symbolism and awkward notation. I might also mention that we can work out products and quotients as well, and function of a function can all be introduced at this stage based on what I've shown you there. So I'd like to pause there then and ask if there are any questions.
Thank you so much, Ken. Any questions, any comments, anything is welcome right now.
In the slide of y equals to 1, I didn't got the concept.
Yes, to follow the pattern, y equals x squared, y equals x, y, we have to have y equals 1. If you like, it's x, it's 1x to the power 0, just the power's going down by 1, and x to the 0 is 1. So the corresponding equation to follow this pattern is y equals 1. And if you want the area under it, from x is 4 to x is 5, then what I'm saying is you can work out the area of this big rectangle, which is 5 times 1, minus the area of the little rectangle, which is 4 times 1, and that's that there.
Any other questions?
I wanted to know what is the difference between integration and differentiation.
Like you said that integration is the opposite of differentiation, but I didn't understand that.
Right, well, I haven't really covered that here, but it is true that integration and differentiation are opposites of each other, and this is explained more in my book and in the course. We'd have to go into algebra here, but you can show that if you express, if you can see where I'm indicating here, if you express this algebraically, you get a third x cubed, and that if you differentiate a third x cubed, then you get x squared, and that's how these are connected. I haven't really gone into it here, and it would take me a few minutes to explain and go into this algebraically and show the connection. But what you're talking about is what's called the fundamental theorem of calculus, which is that the antiderivative, as it's called, what you get when you reverse differentiation, actually gives you areas under curves.
Jyoti
I do have a question.
Yeah,
I'm
sure.
here. Can you hear me?
Yeah, we can. Yeah.
Okay. Well, Ken, as such, I teach economics 2 class 12, and there are certain formulas in which they have to find out the national aggregates. So, is there any way, like by which we can connect those formulas through the Vedic maths technique? Regarding that, would it be okay if I can send you an email of the formula and we can go do some research on that?
I didn't hear that very well. There's a child talking. You're talking about some formulas. What formulas were they again, please?
Regarding calculating of national aggregates for our country.
Regarding what?
Regarding national aggregates such as domestic, gross domestic product, then net national product. So there are certain formulas in economics. If we can relate that to Vedic maths.
Right, well, that would be very interesting. We're always looking for opportunities to expand the range of Vedic mathematics in other areas. So if there are specific formulas in economics or anywhere else, we'd be very happy to hear from you so that we can see how they might connect up. Perhaps
Sure,
you could
sure.
send me an email or communicate somehow. Very glad to see that.
Sure, that will be the best. And I'll send you an email of all the formulas, and I would really like to connect them with the maths.
Fantastic, thank you. I look forward to that.
Yeah, is there any certificate course for the Vedic mathematics?
Yes, we have several. You should look on my website under the courses. We do a teacher training course which is very popular, and we're running one at the moment, and various other courses as well, including one on calculus.
Okay, and what is the procedure for that?
Right, well, if you go onto the website, and my website, I hope you know where it is, click on courses, and then you can select the course you're interested in, and you'll see what to do. It's all explained in the web page.